I'm using the MNIST dataset, a classic collection of handwritten digits. It's split into training data, X_train, Y_train, to teach the model, and testing data, X_test, Y_test, to evaluate its performance. Think of it as providing examples for the model to learn from. The main goal here is to build a system that can accurately identify which digit, 0 to 9, is written in each image from the MNIST dataset. It's a common machine learning problem. This is one of 3 models I'm using to analyze the image data. It's a simple and efficient model for classification. I'll use its prediction. Another model. Support vector machines are powerful algorithms that find the best boundary to separate different classes of data, in this case, different digits. Its predictions are an input to another model. This is my third model, an ensemble method, combining multiple decision trees to create a powerful classifier. Each tree gives a prediction, and their collective result contributes to the system. These are the MNIST dataset's variables. X_train and X_test contain the images, features. Y_train and Y_test contain the correct digit labels, the answers, associated with those images. This is the model that combines predictions from the 3 base models mentioned above, logistic regression, SVM, and random forest. It uses their collective strength to make the final decision on digit identification. In this case, it's gradient boosting. This is a specific type of machine learning model from the Sklearn library that uses multiple base models, here, logistic regression, SVM, and random forest, and combines their outputs using another model, gradient boosting. It's like having a team of experts voting on a decision. I use StackingClassifier.fit, X_train, Y_train, to train the model. The model learns patterns from the provided training data, X_train, Y_train, so that it is able to make predictions based on unseen data, X_test. The result is a trained model ready to classify new, unseen handwritten digits from the MNIST test set, using the best strategy that incorporates the strengths of multiple models for better accuracy. Awesome! This question tests your understanding of how to set up and train a StackingClassifier in Sklearn. I'm checking if you know how to correctly use base estimators and a meta learner, and understand optional settings such as StackingMethod and CV. Here, I define a list of base estimators, logistic regression, LR, support vector machine, SVM, and random forest, RF, each paired with its name. Then, I create a StackingClassifier using these base estimators and gradient boosting, GB, as the final estimator. Finally, I train the classifier using the training data. This option is similar to A, but I explicitly set the StackingMethod to predictproba. This tells the StackingClassifier to use probability predictions from the base estimators, which often leads to more accurate results. Again, I train using the training data. In this option, I'm doing the same as in options A and B, but I've added. This performs 5-fold cross-validation during training. Cross-validation helps avoid overfitting and generally gives better performance, so this is often the preferred approach. This option is incorrect because I don't provide names for the estimators in the ESTIMATORS list. The StackingClassifier expects each estimator to be given a name within a tuple, like LR. This refers to the StackingClassifier, a machine learning model from the Sklearn library that combines multiple base estimators, like logistic regression, SVM, random forest, to create a more powerful ensemble model. A meta-learner, like gradient boosting, is then trained on the outputs of the base estimators to make a final prediction. This is a simple and efficient classification algorithm. LR is just an abbreviation. A support vector machine, SVM, is another powerful classification algorithm, effective for high-dimensional data. Gradient boosting, GB, is a meta-learner that works by combining multiple weak learners to create a strong predictive model. A random forest, RF, is an ensemble learning method that combines multiple decision trees to improve prediction accuracy and robustness. In stacking, the meta-learner learns from the predictions of the base estimators to make the final prediction. Think of it as a teacher that learns from the students' base estimators to improve its own performance. This is the core of the question. We're learning how to construct and use it in scikit-learn. I'm using scikit-learn's StackingClassifier to build a model that combines multiple learning algorithms. It's like having a team of experts each working on a part of the problem and then having a supervisor, meta-learner, to combine their individual assessments for the final answer. This question challenges you to write the correct code to use this powerful model building technique. We'll explore several options, and I'll guide you in choosing the best one. This is one of the base estimators. It's a simple, yet powerful, algorithm I use for prediction. Think of it as one of the experts on the team. Support vector machine is another base estimator in my stacking ensemble. It's great for finding the optimal separation between data points. Another expert. This algorithm is the meta-learner, the supervisor, of my team of experts. It combines the predictions from the base estimators and produces a final result. It leverages the results of the others to make a more powerful prediction. This is another algorithm I use as a base estimator. Random forests use multiple decision trees to improve accuracy and reduce overfitting. One more expert in my team. I'm defining a list of my base estimators, each with a name, LR, SVM, RF, and the model itself. This is what I feed into the stacking classifier. It's the list of experts. This shows an incorrect approach. I'm missing names for the base estimators. Oops. Each needs a label. This is the best option. I've correctly named my estimators, specified the meta-learner, and importantly, used 5-fold cross-validation. =CV equals 5 =. This helps prevent overfitting and makes the model more robust. It's my winning strategy. I'm using 3 different machine learning models, logistic regression, support vector machine, and random forest, as the base estimators for my stacking classifier. These models will individually make predictions on the input data. Think of them as individual experts providing their opinions. The gradient boosting model acts as the meta-learner or the judge. It takes the predictions from the base estimators and combines them to create a final, hopefully improved prediction. It learns from the strengths and weaknesses of the individual experts. Here, I'm defining a list of tuples. Each tuple represents a base estimator. The first element of each tuple is a string name, e.g., LR, for logistic regression, and the second element is the actual model object, e.g., the trained logistic regression model, LR. This structure is how I tell the stacking classifier what models to use and how to refer to them. Cross-validation is a technique to evaluate a model's performance more robustly. =CV equals 5 means I'm using 5-fold cross-validation. The data is split into 5 parts. The model is trained on 4 parts and tested on the remaining part, and this is repeated 5 times with different parts held out for testing. This helps prevent overfitting and gives a more accurate performance estimate. Instead of just getting the final class prediction from each base estimator, the =stack_ method equals predict_proba. Option tells the stacking classifier to use the probability estimates instead. This usually gives a more informative input to the meta-learner, resulting in potentially better overall performance. The meta-learner can weight these probabilities and make a more informed decision. Logistic regression is a linear model I am using as one of my base estimators. It models the probability of the different classes. The support vector machine is another model I use as one of the base estimators. It tries to find the optimal hyperplane to separate data points. The random forest is an ensemble method that creates multiple decision trees and combines their predictions to achieve higher accuracy and robustness. I am using this too as a base estimator. These are my training data. *x_train contains the features, the pixel data of the handwritten digits. And *y_train contains the corresponding labels, the actual digits. These are the predictions made by both base estimators and the final model. This is the output of the classifiers. I see this as the overall structure of how we combine multiple machine learning models. Imagine it like a team of experts, base estimators, giving their opinions, and then a super expert, meta learner, combining those opinions to make the final decision. These are the individual machine learning models that we use to get initial predictions. In this problem, we have three: logistic regression, LR, support vector machine, SVM, and random forest, RF. Think of them as the individual team members. This is a linear model. It finds the best fitting line to separate data points of different classes. It's a simple but often effective model. This model finds the optimal hyperplanar boundary that maximizes the margin between different classes. It's known for its good performance in high-dimensional spaces. This model combines multiple decision trees to improve accuracy and reduce overfitting. It's like getting multiple opinions and averaging them out. This is the final model that combines the predictions from the base estimators. Here, it is a gradient boosting classifier, GB. It's our super expert who makes the final call based on what the others said. This is an ensemble learning method that sequentially builds trees, where each subsequent tree corrects the errors of the previous ones. Think of it as refining the combined opinions to get a more accurate answer. This is the data we use to train our models. X_train contains the features, handwritten digit images, and Y_train contains the correct labels, the actual digits. We're teaching our models using this data. These are the combined predictions from the base estimators. Think of it as the individual team members' answers before the super expert makes the final decision. This data is used to evaluate how well our trained model performs on unseen data. X_test contains new images, and Y_test contains their true labels. This is our test of the team's overall performance. These are the final predictions from our stacking classifier model on the test data. It's the final answer from our super expert. These are the results after all the models have done their work. I see a stacking classifier, which is like a team of different classifiers working together. Each one makes its prediction, and then a final classifier combines those predictions to make the best overall prediction. It's a powerful way to boost accuracy. These are the individual classifiers on the team. In this problem, we have logistic regression, LR, support vector machine, SVM, and random forest, RF. Each one makes a prediction based on the input data independently. This is a simple yet effective classifier. It learns a linear relationship between the input features and the output class. This one finds the best hyperplane to separate data points into different classes. It excels in high-dimensional spaces. This is an ensemble method. It combines multiple decision trees to make a more accurate prediction. Think of it as a group vote among many experts. This is the final classifier in the stacking classifier. It takes the predictions from the base estimators as its input and learns how to best combine those predictions for a final, hopefully improved prediction. In this case, it's a gradient boosting classifier. This is another ensemble method that builds a tree at a time, sequentially correcting the errors of the previous tree. It's powerful and often very accurate. This is our dataset. X_train contains the image data, the features, and Y_train contains the corresponding labels, the digits 0 to 9. We'll use this data to train our stacking classifier. This refers to the output of our classifiers. The base estimators and the final estimator output predictions for each data point in the MNIST dataset. This is one way to set up the stacking classifier. It's correct, but I might prefer option B or D, which offer improvements. This improves on option A by using prediction probabilities instead of just class labels. Probabilities give the classifier more information to work with. This is incorrect because it doesn't properly define the base estimators. I need to give each base estimator a name. This is the best option. It correctly sets up the stacking classifier, uses probabilities, and includes cross-validation, CV equals 5, making it more robust and less prone to overfitting. I'm using Scikit-learn's StackingClassifier, a powerful tool for combining multiple machine learning models. It's like having a team of experts, each with their own special skills, working together to solve a problem. Pretty cool, huh? This question challenges me to correctly set up and train a StackingClassifier using different base models and a meta-learner. I need to get the parameters just right. This option shows one way to initialize the classifier. It sets up the base estimators correctly, but it misses some opportunities for improvement. Here's another attempt. This is better than option A because it uses probability predictions, which often lead to more accurate results. This code is incorrect because it fails to provide names for the individual estimators, a requirement for the StackingClassifier. This is the best option because it uses cross-validation. Cross-validation helps me create a more robust model that generalizes better to unseen data. The magic of prevents overfitting. These are the individual models: logistic regression, support vector machine, and random forest, that act as the experts in my stacking ensemble. Each brings a unique perspective to the problem. One of my base estimators, logistic regression, is a simple yet effective model. It predicts probabilities based on linear relationships. Next, I've got the support vector machine, known for its ability to find optimal separating hyperplanes in high-dimensional spaces. Finally, the random forest, an ensemble method itself, brings its strengths of randomness and averaging to the table. This is the gradient boosting model. It takes the predictions from the base estimators and learns to combine them optimally, leading to even more accurate predictions. This is my meta-learner, a powerful model that will learn the best way to combine the predictions of the three base estimators, producing a stronger model.